Right, in this video I'm going to be going over some of the details of the pendulum, in particular how we determine the period of a pendulum. So what you can see on the screen in front of you now is a simulation of a pendulum swinging back and forth. So all it is a mass attached to a string, which is attached to a point at the top, and the pendulum is displaced from equilibrium, so I'll just stop it. So if I displace the pendulum from equilibrium and release it, it'll swing back and forth around the midpoint, the equilibrium position, and the period will remain constant. And we're going to be looking in particular today at how we can determine the period of a pendulum. So I'm going to pause that, and we'll go back, and we'll just create some basic notes here. So this is the pendulum. And that's an example of SHM. So what we'll do in this video is we will show that the pendulum is undergoing SHM. We will learn the equation for the period of a pendulum. We will use the equation to solve problems, and we will also show why the equation takes this form. Okay, and the key thing here is for our learning is to become really good at these things, because those are the things that we're kind of mainly going to be asked to be able to do in this course. So firstly, let's have a look at simple harmonic motion. So SHM and the pendulum. Okay, so we need to remember that for SHM, an object's acceleration must be proportional to its displacement from equilibrium and in the opposite direction to its displacement. Okay, so does the pendulum meet these criteria? So let's just have what we'll do is we'll just have a look at the pendulum, and what I'm going to do is add an acceleration vector here, and it's poised at the moment, so I'm just going to move it around. So if we move it to different positions, we can see that as we get further to the left of equilibrium, the acceleration gets bigger. And now the acceleration, when we're to the left of equilibrium, the acceleration is to the right. So this yellow vector is the acceleration. So the acceleration is in the opposite direction to the displacement at all times. So it's always pointing the opposite way to the direction that we're displacing it, or it's always pointing back towards equilibrium. And it gets smaller and smaller the closer we go to equilibrium, and it's zero at equilibrium. So the further we move it from equilibrium, the larger the acceleration is, which means it's proportional to displacement, and it's always in the opposite direction. So we can say here that a pendulum meets these criteria, and we'll add just as long as amplitude is small. So the reason it has to be small, I'll just go back to the simulation and show this. So if I have a small displacement to the left here, then the acceleration is pointing back towards equilibrium. However, if I make the displacement really big, you can see that now the acceleration is not pointing towards equilibrium. So we've displaced the mass to the left here, but the acceleration is kind of pointing way more down. So it's not exactly opposite to displacement. However, if we keep the displacement small, we can see that it's approximately opposite to the displacement. So the pendulum is a simple harmonic oscillator as long as the amplitude is small. Okay. So if we're ever doing an experiment with a pendulum and simple harmonic motion, we should be careful to keep the amplitude small, otherwise our equations will only approximately work. Okay, now a couple of points to make about the pendulum is that the period of a pendulum is constant. And independent of mass and amplitude. So I'll show what I mean by that. So if I add a period timer here, so this will time one period. If I set this thing swinging, we can see, in fact I'm going to get rid of that acceleration vector now because it's distracting. So it's swinging back and forth, and I'll set the period timer to go, and it'll time one period for me. We can see that the period is approximately 2 seconds. Okay, if now I make the amplitude bigger, we can see that the period is still approximately 2 seconds. So it's moving much faster, or it's moving faster through its cycle, and the speed of it kind of accounts for the fact that it's also moving further. So it doesn't matter if we make a tiny amplitude, we can see that the period is still 2 seconds. If we make it slightly bigger, it's still 2 seconds. So the amplitude doesn't matter. It doesn't matter if we have a big amplitude or if we have a very small amplitude. The period remains the same. The second thing that doesn't matter for a pendulum is how much mass we have. So if I dramatically reduce the mass here, so now I've got only 200 grams. If I set it swinging now, the period is still 2 seconds. If I make the amplitude small with a small mass, it's still 2 seconds. So one of the cool things about a pendulum is that its period only depends on how long it is. Sort of. Okay, so it is. So this is a key point here, that it's independent of mass and amplitude. Okay. Now we're going to introduce the equation for the period. So the equation for the period of a pendulum so we can say that T is equal to 2 pi square root L over G. This is the equation, so we can say where T is the period in seconds, L is the length, and that's from the pivot to the center of mass in meters. And I say from the pivot to the center of mass. If we have a big sort of metal mass at the end of a light string, then that is going to be pretty much exactly the length of the pendulum, because the center of mass is going to be in the middle of the block of metal. But if you have something like a stick that's swinging back and forth, or a chain, then the center of mass is going to be a bit higher. So we'll talk a little bit about that later on. Okay, and G is the acceleration due to gravity. In meters per second squared. All right. So the next thing is, what does this mean? It means that if we increase the length, the period should, well, if we make L bigger in this equation, then the period is also going to get bigger. The period should get longer. And if G is stronger, so we're on another planet, for example, that's the gravitational field. So that's kind of depends on, if you were on the moon, for example, you'd have a much smaller G. But if we had a bigger G, then the period should get shorter. Okay, we'll have a look and see what that looks like here. So if we, I'm going to reset this whole thing. I'm going to set this thing swinging. So here we can now time this period here, just so we know how, as a reference. So the period here is about 1.7 seconds. So we now have a length of 0.7 meters, and we have an acceleration, we're on Earth here, of 9.81 meters per second squared. Okay, so now if I increase the length here, or no, I'll increase the length to 1 meter, we can see that now the period is 2 seconds. So a longer length means that we get a longer period as predicted. If we decrease the length to like 0.3 meters, we can see that we end up with a much shorter period. So clearly increasing the length increases the period. Okay, the second thing that we wanted to check, so I'm going to go back to this default setting and add the period timer, and it was about 1.7, I think. So about 1.7 seconds. If instead of this, I change so that we're on Jupiter, if we could stand on Jupiter, Jupiter has a much bigger mass and therefore a much stronger gravitational field. So if I set this thing swinging now, and I time it, it has a much shorter period, because G on Jupiter, instead of being 9.81, is 24.8 meters per second squared. So the strength of the gravitational field also affects the period. So what we'll do is we'll have a look at an example. No, actually first we'll just check out why it is this. So why does it look like this? Why does this happen? Okay, and what we'll do is we'll have a look at firstly we'll focus in on the first one, because most of our experiments are going to be done on Earth. So in most of our experiments, G is going to be 9.81. Okay, so if we look at a long pendulum here, so if we imagine we have a really long pendulum like this, then at this moment our displacement is this, x, and what that would look like, what the forces would look like on here, is we have a weight force acting downwards and a tension force acting at an angle like this. So in this situation, so this is the weight and this is the tension. So the restoring force in this situation is going to be the net force acting on the thing, which is going to be this force here. So this is the restoring force. And for a long pendulum, that restoring force is small for this particular x. If we have a shorter pendulum, then our diagram would look like this. Oops, I'll stick to the same colors. Then our diagram would look like this. And we have the same x here, so the same displacement. So, but in this case, at the same displacement, our pendulum, the force diagram would look like this. We'd have the same weight force because we have the same mass here, and we'd have a tension that acts in this direction. And if we add those two up, sorry, that tension should be a little bit longer here. If we add those two up, we end up with a much bigger restoring force. And we can say then, for a shorter pendulum, the restoring force is bigger. So acceleration is greater. So period is shorter. So, and this is for the same displacement. So we can say for all displacements. F is bigger. So it's because in order to get the same displacement, we need a larger angle for a shorter pendulum. So this is a long pendulum, and this is a short pendulum. So that kind of explains why the length of the pendulum changes it. The strength of the field, the strength of the gravitational field, I'll just mention briefly because it's slightly less likely to come up. If we have a stronger field, then of course this downwards weight force is going to be bigger. So we're going to end up with a longer downwards arrow, and therefore a longer tension, and therefore a longer restoring force. So a stronger field will also increase the restoring force. Okay. So now we'll have a look at a couple of examples of how we would apply this equation. So, examples. So 1. So just a straightforward application of the equation would be if we have a pendulum of length 1 meter, what would its period be? Okay. In this case, it's just a straightforward application of the equation. We can say t is equal to 2 pi square root L over g, which is 2 pi times square root 1 over 9.81, which gives us a period of 2 times pi times 1 over 9.81, and I will square root that, and we get a period of 2.0 seconds. Okay. And we can say an interesting second example would be if we took this pendulum to Mars, its period would be 3.22 seconds. Let's just make it 3.2, and we can stick to two significant figures. What is g on Mars? So this would be a valid method for working out the gravitational acceleration on another planet. Okay, so what we need to do here is we need to recognize that it's g that we're trying to find out, so we write the equation t equals 2 pi square root L over g, and then we need to rearrange it so that g is the subject. So we'll square both sides. To get rid of that square root. Then we'll multiply g to both sides, and we get gt squared is equal to 4 pi squared L. And then we divide by t squared to get just g on its own. So g is equal to 4 pi squared L over t squared. And it was the same pendulum, so it has a length of 1 meter. So g is going to be equal to 4 pi squared times 1.0 divided by the period that we were given, which is 3.2 squared. So that should give us the acceleration due to gravity on Mars. So we go 4 times pi squared times 1 divided by 3.2 squared, which gives us 3.9 meters per second squared. So we can find that as well. One little detail that I want to just mention, because it does pop up every now and again, is, and it's good to know that actually the length of a pendulum is the distance between the pivot and the center of mass. So a girl on a swing stands up while she is swinging. What happens to her period? What happens to the period of her swing? Okay, and in this case, what we need to do is just, I would quote the equation first. T equals 2 pi square root L over G. And then we can say, as she stands up, the center of mass of the swing moves closer to the pivot. This means the length of the pendulum, because the swing is a type, I'll put pendulum, swing is a type of pendulum, decreases. So the period of the swing will decrease. Okay, so that kind of shows how we can apply the equation to some situations. Obviously, you need to get quite comfortable working with the equation. So you do need to solve a few problems, and there's a simulation task for you to do on the pendulum that will allow you to kind of work with the equation a little bit. So just to summarize, the period of a pendulum depends on L and G and can be determined using T is equal to 2 pi square root L over G.